Let's do a little bit of physics X. Okay, you're allowed to ask me any question you want, and I will do my best to answer it intelligently, and if I can't, we'll just edit it out and put Carl Sagan back in here. Jamie.
Okay, so why is light affected by gravity, and why can't light be slowed down?
Excellent questions. Okay, so let's see if we can attack the first question, right? Light being affected by gravity. So the idea is this: if I have a distant star and it's emitting light in all directions, some of that light will eventually come here to Earth and be detected by us. Maybe it's a detector in your telescope. Maybe it's your eyeball, right? It's kind of weird just thinking about that whole process. This photon that left this atom in that star traveled across the universe, came through our atmosphere, and when you looked up and saw that star, you grab that photon, and guess what? When you detect the photon, you destroy it. It's gone forever. So that poor little photon that just traveled all the way across the universe, you just destroyed by seeing it. All right? Now the idea that, one, it just takes a long time for that to happen is kind of interesting, because light takes time to travel, right? It doesn't travel at infinite speed. It travels at finite speed. And so when you look at distant stars, you're actually looking back in time. And one of my friends, who's a starving actor in Los Angeles, he said, you know, when astronomers tell us that you should wish upon a star, they're really lying to us, because that star has actually been dead for millions of years, just like your dreams. All right, what was the question? Oh, the question was, right, what happens to light when it gets near gravity? So let's pretend we have a very massive object right there. Pretend it's a black hole. Okay? Light that left that star, which would normally miss us entirely, is in fact bent by that black hole and comes and hits us here on Earth. Okay? Light itself is affected by gravity. Now, how do you explain this? The way they explain it in general relativity is black holes and any object that has mass, in fact, creates a curvature in space-time. And so if I think about this black hole sitting on this sheet of space-time, what it really does is it bends space-time locally. And it's just like you put a bowling ball on a sheet. Okay, if you spread a sheet out over your bed and you put a bowling ball in the center, the sheet kind of curves in. And if I roll a marble along, when it goes past that curvature, it's going to arc, right? It's going to bend. And that's what happens to photons as well, because photons have to travel through space-time, and they try to take the shortest path through that space-time, and that turns out to be shortest path when you curve it just so. Now that's how they explain it in general relativity. But there's another way to explain this, which I think is kind of cool. Let's say we put our object right there, and maybe it's a black hole, and we send some object past that black hole. If that object has mass, then of course it's going to get bent by the gravitational field of that black hole, right? We understand that. That's just gravity. But is there a photon mass? No. But you can kind of think about a photon mass in the following way. A photon has energy. And that energy is related to an effective mass by the most famous formula in physics, E equals mc squared. And so you say, what's the mass of a photon? It's that. It's its energy divided by c squared. And we're going to have to be clear that we're talking about this moving mass, this moving inertia of the photon. So a photon having energy, you can consider it having mass when it moves. And since mass is affected by gravity, it gets bent by the black hole. Okay, so Jamie asked a question about slowing down light. And let's frame that question in relation to recent experiments that you maybe have heard about. In the last 10 or 12 years, a lot of these experiments have been done, and you might have heard in the news things like slow light, or fast light, or stopped light. Okay? And the idea is the following. Light itself exists at c, and that's it. Okay? It just moves at 3 times 10 to the 8th meters per second. But when you talk about slow light, what are you really talking about? You're talking about the following. If I take a pulse of light and I send it through a box, it's going to come out the other side. And what it looks like to you is it went slower through the box than it should have if there was no box. Okay? And this is our slow mechanism. There has to be stuff in the box to make that happen. What's in the box? A whole bunch of atoms and molecules that you prepare in a very specific way. All right, so maybe people are okay with that, right? It comes out slower, the propagation is slower than c. What about fast light? Fast light is the following. Here's my box with fast stuff in it, and when that pulse comes out, it has now moved faster than the speed of light. And that's kind of weird to think about, right? I put in a pulse, and if the box wasn't there, it would have come out somewhere in time, but in fact, with the box there, it came out ahead of that. It came out faster than c. And in fact, you can do this last experiment. You can stop it. Pulse of light goes in, it stops in the medium. And in fact, you can just hold it in there for a while, and then you can flip a switch and let it go again. So that's called stopped light. So here's the catch. The speed of light is always c. It's always 3 times 10 to the 8th meters per second. So what are we really talking about when we say slow light, fast light, or stop light? What we're talking about is the interaction with atoms and molecules can make it look like your pulse of light in fact went slower than light, faster than light, or stopped altogether. But if you take away the atoms and the molecules, it always exists at c. It always moves at c. And there's a caveat to Einstein's theory of relativity. Einstein didn't really say that nothing can move faster than the speed of light. The way we interpret that now is you cannot send information faster than the speed of light. And so even in the case of fast light, there is in fact no information that you can put on this pulse that will come out the other side faster than the speed of light. And that's a very subtle interpretation of this experiment, and it's very difficult conceptually. But just know that currently, you cannot send any information faster than the speed of light. Even though it looks like this pulse went faster than the speed of light, there's in fact no way to put information on there that comes out faster than the speed of light.
Wait, so if no information can go faster than light, what does?
Exactly. Good question, right? Because isn't this a pulse of light? Isn't that like a bit? Right? I mean, usually when we talk about bits, it's on is 1 and off is 0. So isn't that a bit of information? And the answer is the following. If I put a little information in here, like a dip, right in the center, it doesn't come out there. It is complicated by this, and what happens in this experiment is the leading edge of that pulse, in fact, triggers this exit pulse. That leading edge becomes the whole pulse, and if you look at that compared to that, it did not travel faster than the speed of light. And this actually took a long time to sort out. Scientists debated the implications of this experiment for quite a few years, but that's the current understanding, is that the leading edge, in fact, becomes the whole pulse itself. And it's very much more complicated by what's in the box. That's really the hard part of the experiment. If you're totally confused, then that's good. You've been listening. I'm okay with that. All right, excellent question. Anything else we should talk about before we should get out of here? Thank you for the question, Jamie. Have a great day.